Okay, so we're going to be going over physical, chemical changes, reactions, how we graph. Make sure we're taking notes right now, please. No social media. And we've already gone over this briefly. Phase changes have a very specific graph, right? Kinetic, potential, kinetic, potential, kinetic. This happens to be a heating curve. This one is endothermic. So this would indicate endothermic phase changes of melting and boiling. And I can also have the opposite, a cooling curve. There we go. This will be exothermic. Overall heat is leaving the system. And this would be for condensation and freezing or solidification. Okay. So these would be phase changes. We know phase changes are physical changes. And now we're going to focus on chemical changes, which have a very different graph. Remember, these were temperature-based or kinetic energy-based. Right? Kinetic energy is changing. If kinetic energy is not changing, then potential was. Last look here. And any questions? Otherwise, we're going to go to chemical changes. And this is the new stuff. So chemical changes have a very different graph. We're going to look at a generic and label it because you do need to memorize this. Okay, so let's take a look. Okay, so you can see this looks like a roller coaster. Chemical changes will have that roller coaster look to them. We always start off with the reactants and we always end with products. Again, we're writing because we have to memorize. And writing things down helps us memorize, especially if you're like me and a visual learner. Even non-visual learners, this does help. Okay, so we have reactants, we have products, we have this in-between state. This in-between state is called the activated complex. Okay, so I'm going to go grab that, get your notes. Okay. So I have a visual for you. Okay. So we start off with reactants. If everybody can look up here, literally look up here. Literally at home too. Stop looking at whatever you're looking at. Look at me. So let's start with green. Watch what happens. Not enough energy. Still reactants. I put enough energy into it. Oh, not enough orientation. Cool. Let's try it again. Nope. One more time. Come on. Good Lord. Okay. Let me throw it to somebody else. Let's see if that helps. There we go. Throw it back. Okay. So let's see if I can do it up here so people at home can see. I don't know. There we go. It switches over. And I'm going to try to show. It's hard to show you guys at home because you can't see the whole range. Maybe if I move it back. But I want you to see, notice what happens when I let go. How it opens up. That's the transition state. That's the activated complex. It's not a reactant. It's not a product. It's in between. Okay? That in-between state is your activated complex. And it's very complex. Like if you go on to college studies, this activated complex could be 10 steps long. I mean, it's very intricate. But we're simplifying it and saying it's in-between state. Okay. How do we get there? We have to add energy. So from reactants up to that point, from here up, that's the activation energy. And we can make a little note of that. Activation energy. Energy of activation. E is energy. The little a is activation. And that's how you're going to see it written. So notice it doesn't start at the bottom. It starts at the reactants. It's how much energy you need to add to the reactants to get to the activated complex. Another big thing that we need to know is the difference. The difference between the products and the reactants is called delta H. Okay? That difference. Now, we don't care about the hill overall. We care about how it starts and how it ends, and that's called delta H, or your heat of reaction. Rxn is reaction. And it can be either positive or negative, depending if are you adding energy or losing energy. So we're going to have to memorize this. Whenever you get a graph, you're going to be labeling it. Reactants, activation energy, products, heat of reaction. Activated complex is less important. We really care about that only because of the activation energy. Okay. We're going to do a couple problems. So last looks. Let's do some comparison. Okay, we're going to compare two graphs so we really get a good feel for this. We're writing. We're not looking at social media. We're not working on other classes that we didn't do homework for over the weekend. We're not taking naps or breakfast at home. Okay, this is stuff you need to know. Okay, so let's take a look. We still have reactants. We still have products. So let's make that clearer. Make it more clear. Products. Reactants, products. And in both cases, we're talking about a forward reaction. Now, notice overall, this is going downward. Okay. Ignore the hill. Overall, this is going upward. Ignore the hill. Overall, when it goes down, that's an exothermic change. When the products are lower than the reactants, it's exothermic, and your delta H will be negative. Will be a negative number. Overall, this is going up. This is going to be endothermic, and that will make your delta H overall positive. So right at a glance, this could be burning wood. This could be a chemical ice pack. Okay? Okay, so make sure you know how to read these things. Let's take a look. One last thing. Again, that delta H. That delta H is going to be the change in the products minus the reactants. Okay, delta H, and here, delta. You can always find those two. Delta H, or heat of reaction, is going to be important. There's a whole table on it, table I. Table I will tell you the delta H reaction. Rxn is reaction for many, many different chemical reactions. It has a whole list. And on there, it will remind you at the very bottom that exothermic will have a negative delta H. So if you ever forget, you look up table I, it will tell you that. The other thing you need to know about delta H of the reaction, it's always products. Always products minus reactants. It's reverse. Final minus initial. And you're going to find that a lot in science. So we always take the end first and subtract the beginning. So to get the correct delta H, products minus reactants. If you do it in the opposite direction, you're going to get it wrong every time. And we're going to do one problem together, and then you're going to practice some using the Edpuzzle. Last looks. Okay, so I'm going to give you a practice graph and some questions. Okay. Let's do 10, 20, 30, 40, 50, 60, 70. And these are kilojoules. This is potential energy. Notice we're measuring potential energy only, not kinetic. Kilojoules is a way of measuring energy. And what I want to know, here are my questions. So the questions are, 1, what are the reactants? I want the reactants. 2, I want the products. 3, I want the delta H. And 4, I want the activation energy. I want amounts. I want actual numbers. So I want reactants, products, heat of reaction, and activation energy. And I want actual numbers based on this. And then I also want to know if it's endo or exo. Okay. Take a few minutes. Sorry about the glare. Again, it's going by tens. Try to give you some key points. If you've been paying attention, this should be fairly quick. Okay, hopefully. Let's check your answers, please. The reactants, right? If I label my graph, I'm going to get this right every time. My reactants are 20 kilojoules. It's right here. My products, what I end with, I go over, and that's 50. So first thing I do is I label my graph. Everything else becomes easier. Delta H, I take the reactants, I take the products, and I make a big triangle. Remember, products goes first. So 50 minus 20 will give me positive 30. If you don't have the positive, you will get no credit. You have to indicate if it's positive or negative with an actual plus sign. Now, activation energy starts at the reactants and goes to the top of the hill. Well, the top of the hill is around 65. So from 20 up to about 65 is about 45. So again, I start at the top of the hills around 65 minus the reactants, and I get about 45. If you had 44 or 46, that would be okay. But make sure you know how to get there. Again, it's the reactants to the top of the hill, not from the bottom. It's not 65. It's 65, take away the 20 from the reactants. And last, overall, this was going up, and it's endothermic, plus I can tell because it's positive that it's endothermic. Okay, we're going to keep practicing this with your Edpuzzle, so good luck.